This is Electric Universe Eyes, and today I'm going to narrate from shmoop.com a study guide titled Types of Bonds and Orbitals, Bonding, Covalent and Ionic Bonds. Get ready for some bonding time. Ever feel overwhelmed with tests and homework? Do you wish you could balance all the things in your life a little better? We all need some stability in our lives. Atoms need stability too. Atoms are constantly trying to complete their outer shell, find balance, and they will lose, gain, or even share electrons in order to receive maximum stability. In order to complete their outer shell, some atoms give electrons, some atoms share electrons, and some atoms steal electrons. An atom's placement in the periodic table dictates what kind of personality that atom is likely to have: a giver, sharer, or a stealer. Exactly what type of bonds are formed between atoms to create compounds? Here are some general guidelines to apply. Metals plus nonmetals equal ionic bonds. Nonmetal plus nonmetal equal covalent bonds. Metal plus metal equals metallic bonds. Ionic bonding. An ionic bond is held together by the electrostatic attraction between ions that are near one another. Electrostatic attraction is the attraction between atoms that have opposite charge and hold the atoms together in ionic bonds. Think of it as an atomic glue. In this type of bond, one atom gives up electrons and becomes a positively charged ion, or a cation. Another atom dons a ski mask and steals the electrons to become a negatively charged ion, anion. Okay, maybe steals is a bit harsh. The atom actually accepts or takes the electron that the other atom is giving up. We don't want to be accused of name-calling. Some of our favorite foods have a bunch of ionic bonds sprinkled all over them. Is anyone up for some chips, fries, pretzels, or peanuts? Notice the pattern? Salts, including table salt, are held together by ionic bonds. Table salt is made of sodium chloride, or NaCl. Take a look at the periodic table. Notice that sodium is in the first column of the periodic table. That means it has only one valence electron in its outer shell. Chlorine, on the other hand, is in the seventh column. It has 7 valence electrons. Chlorine only needs one more electron to complete its outer shell. Did you play matchmaker in your head? Sodium gladly gives up its extra valence electron to chlorine, which gobbles it up faster than Takeru Kobayashi eats hot dogs. The sodium atom becomes a cation and the chlorine atom becomes an anion. And the two atoms are held together by the positive and negative charges of the ions. According to Coulomb's law, more highly charged ions form stronger bonds than less highly charged ions. Ionic bonds tend to be fairly strong and therefore have relatively high melting and boiling points. Ionic solids are poor conductors of electricity because each electron is localized around a particular atom. Their electrons aren't swimming in the electron pool. As a result, they don't move around the lattice. Ionic liquids do conduct electricity, however, because the ions are free to move around in the liquid phase. Covalent bonding. In the case of covalent bonds, electrons are neither lost nor gained. No ions are formed. Instead, the electrons are shared. This group of atoms must have watched Sesame Street as a kid. Covalent bonding is the sharing of one or more pairs of electrons between nonmetals. Covalent bonds in a molecule are often depicted as a dash. The dash represents the 2 electrons shared between the atoms. The atoms can have a single bond sharing 1 pair of electrons, double bond sharing 2 pairs of electrons, or a triple bond sharing 3 pairs of electrons. There are 2 types of covalent bonds. The first is called a nonpolar covalent bond. This is where the atoms equally attract and share the electrons. An example of this is 2 hydrogen atoms, H-H, sharing a pair of electrons. Each hydrogen nucleus has 1 proton that equally tugs or attracts the bonding pair of electrons. The second type of covalent bond is the polar covalent bond. This is where the 2 atoms in the covalent bond are not the same and the attraction to the electron pair is not equal. The atom with the greater attraction pulls the bonding electrons towards them. As a result, the atom takes on a partial negative charge. The other atom has less attraction for the bonding electrons, and it will take on a partial positive charge. An example of this is HCl. The chlorine atom has a much greater attraction for the bonding pair of electrons and will therefore take on a partial negative charge. This type of bond is sometimes depicted as this. Instead of using a single line to indicate the covalent bond, an arrow pointing towards the atom that has the greater attraction for the electron pair is used. The attractive force an atom has on a bonding pair of electrons is referred to as the atom's electronegativity. It's a measure of how badly the atom wants an electron. Atoms like chlorine and fluorine in that second to last column on the right are desperate for electrons to complete their octet. In fact, electronegativity values have been calculated for all the atoms, so we can see which ones are more desperate than others for that extra electron. A general rule, as we go from left to right on the periodic table, the electronegativity increases, as seen with the NCl atoms above. The electronegativity values can also be used to predict whether two atoms will likely undergo ionic, polar covalent, or nonpolar covalent bonds. This article was written by Shmoop University, Inc.